In the universe, there are two great pillars that explain almost everything. We understand why the Earth orbits the Sun, why compasses point north, even why an atomic bomb explodes. But we don't know what lies at the center of black holes, because there, the laws of physics break down. String theory offers a way to fill that gap. It proposes that the smallest particles are not points, but tiny vibrating strings. Each string vibrates in different ways, and these vibrations determine a particle's properties, like its mass or charge. Essentially, all particles are just different notes played by these strings. There are open strings with ends and closed loops. Closed strings are especially important because they could produce the graviton, the particle linked to gravity. This is why string theory might unify all fundamental forces: gravity, electromagnetism, and the strong and weak forces into a single framework. Strings are incredibly small, about 10 to the negative 35 meters. At this scale, strings aren't just tiny. They behave differently than the point particles of traditional physics. They solve problems like infinite results in quantum calculations and allow forces to unify mathematically. String theory has evolved over decades. In the 1960s, physicists explored strong nuclear forces. In the 1970s, they discovered strings could also explain gravity. By the 1980s, supersymmetry introduced the idea that every particle has a partner, leading to superstring theory, capable of describing both matter and forces. To work mathematically, string theory requires extra dimensions, 10 or 11 in total. Most of these are hidden, compactified at tiny scales, like curled-up folds of space. Their shapes, described by Calabi-Yau manifolds, influence how strings vibrate, which in turn shapes the universe's particles and forces. There are also branes, multi-dimensional surfaces that strings can attach to. Our universe might even be a three-dimensional brane floating in higher dimensional space. All particles and forces except gravity could be confined to this brane, explaining why we don't perceive extra dimensions. Though still unproven, string theory offers a beautiful, unified vision of the universe, turning the diversity of particles and forces into vibrations of a single, underlying object: the string. It's a bold attempt to describe everything, from the tiniest particles to the cosmos itself, in one elegant framework. Far beyond the electromagnetic force, taking into account these extra dimensions could be crucial to explaining unexplained phenomena. Considering these dimensions, we might begin to speculate that phenomena like dark energy or dark matter could originate from them. More simply, these additional dimensions could play a key role in fundamental questions, such as the origin of the Big Bang, the accelerated expansion of the universe, or the properties of exotic particles. For now, these extra dimensions remain hypothetical, but their study is already inspiring major advances. Particle accelerators, like the LHC, search for signs of their influence. Gravitational waves could one day reveal clues about the multidimensional structure of space-time. The takeaway is that extra dimensions are among the most intriguing aspects of string theory. Even if invisible at our scale, they might hold the key to unifying all fundamental forces of the universe. Exploring them, even indirectly, could usher in a new era of cosmic understanding. Now, let's return to a surprising point: gravity. We've seen that this fundamental force is far weaker than the others. Why is that? Have we understood this discrepancy? Gravity, as we know, is universal. It keeps planets in orbit and governs the dynamics of galaxies. Yet it is astonishingly weak compared to forces like electromagnetism or the nuclear forces. String theory offers a fascinating explanation. Gravity might spread across extra dimensions, diluting its effect in our observable space. To illustrate, consider comparing gravity with electromagnetism. A simple magnet can easily lift a paperclip, countering the entire Earth's gravitational pull. This demonstrates that gravity is billions of times weaker than electromagnetism. But string theory suggests that this apparent weakness isn't an anomaly. It's a consequence of hidden dimensions. Gravity, unlike other forces, isn't confined to our four-dimensional brain. Gravitons, the hypothetical carriers of gravity, are thought to be closed strings free to move through extra dimensions, diluting their effects in our universe. Think of it like a flashlight. If its light spreads only across a wall, it appears bright. But if it spreads in all directions of a three-dimensional space, it loses intensity. Gravity might appear weak for the same reason. It disperses across dimensions beyond our perception. So how does this multi-dimensional gravity interact with space-time? Our universe is defined by space-time, a four-dimensional fabric combining three dimensions of space and one of time. According to Einstein, gravity is the curvature of this fabric caused by massive objects, guiding their motion. String theory suggests that gravity's propagation depends on how extra dimensions are structured. One model, the Calabi-Yau model, posits that extra dimensions are curled up at incredibly tiny scales, close to the Planck length. Gravitons propagate through them, but the effect is subtle, barely noticeable in our observable universe. Another model, Randall-Sundrum, proposes that our universe is a brain floating in a five-dimensional space. Gravity is concentrated near our brain, but leaks slightly into the fifth dimension, explaining its apparent weakness while remaining observable. The implications are profound. If gravity spreads into extra dimensions, it affects the formation of galaxies, stars, and planets. Gravitational waves might carry evidence of these hidden dimensions, appearing as unexplained energy losses. Meanwhile, other forces remain confined to our four-dimensional brain because they are mediated by particles like photons or gluons that cannot escape. If extra dimensions exist, they might even allow the formation of microscopic black holes in particle accelerators, which would decay rapidly but could confirm a multidimensional space. Most importantly, multidimensional gravity could be the missing link to unified general relativity with quantum forces, electromagnetic, strong, and weak, into a single framework. Extra dimensions allow equations of relativity and quantum mechanics to coexist naturally, making gravity a natural phenomenon in a multi-dimensional space. In short, gravity's apparent weakness might be an illusion caused by hidden dimensions. It loses intensity in our universe while remaining the dominant force on a cosmic scale. This theoretical framework opens fascinating perspectives on the nature of space-time and the universe itself. Looking more broadly, string theory has radical implications. Our universe could be just one of many, each with its own physical laws, constants, and structures. The multiverse. The existence of extra dimensions influences the very structure of the universe. Different configurations of these dimensions produce distinct universes, each with unique laws of physics.